Okay, before we even start, stop writing down whatever you're doing. Everything I will do in this video, you'll have this link in the description, and I'm going to post all these notes, and you can have them too. Okay, well, this video is mainly going to be about knowing which one of these equations to use, when to use them, and which one not to use for a question, right? Because usually we always know how to use these, but we don't know when to use them, and that's when we get things wrong. Common questions I often come upon is, which one do I use? How do I know if it's positive or negative? And why is gravity positive? Because sometimes gravity will be positive, which makes no sense when you first start learning physics, but when you start doing more physics problems, you'll actually see that sometimes gravity, we should call it positive. Yeah, and the deeper understanding of these equations comes from this part right here. So this first half of the video, I'll be showing you where this equation comes from, and this equation, and this equation, and then the second half of this video, I will do a problem, and I'll do another problem. Now, there's only two problems, but they'll cover every single equation used, so you're going to see them in action. Well, enough said, let's start. Okay, so this is your famous kinematic equation. You've probably seen this and wrote this down 100 times, but you probably don't know where it comes from. Okay, now, if you have an initial velocity VO and a final velocity V, and given acceleration is constant, meaning acceleration is not like it means as long as acceleration is not slipping like this, and acceleration is just slipping like this, or like this, um, a box, as long as acceleration is not changing, it's just some sort of constant, right? You can use this equation. And also assuming that, you know, everything you do starts at TO, so it starts at the beginning of time and time goes on, which really just means you're not breaking any sort of weird laws. You're not traveling through time. Okay. So let me show you. Okay, well, let's just start off with the fact that v is equal to dx dt, right? Velocity is equal to the change in position divided by the change in time. Okay, and that's all good. We like that, right? Okay, what else do we know? We know that acceleration is equal to what? The change in velocity over the change in time. And another way to say that is d squared x dt squared, right? Or it's a second derivative of position. Okay, and these are just things we know. So when I come about this equation, we're relying on these two concepts here. Okay. Okay. Now I'm going to show you how to get this equation. And guess which one we use. Do we use this one or do we use this to find this equation? Well, if we use this, we'll never find A. If we use this, we do have A, right? So we're going to use this one to find this equation. And by the way, what we're going to do right here is actually a technique called separable differential equations, right? Like you'd learn the separable technique in a class called differential equations, which is probably far out from where you are right now, but you're going to learn a little bit of differential equations right now. And it won't be that terrible. Okay, so what we can do first, we're going to draw this arrow for indicating that we're going to change something. So let's just write A is equal to dv dt, but then let's multiply out the dt and put it on both sides. Okay. So in other words, I have A dt is equal to velocity. Okay, and real quick, before we even move on, units for acceleration is meters a second squared. Units for time, right? This means this the dt, it still has units t, right? It still just, I mean, it still has units seconds, right? It just has units second. So then this is equal to what? Meters a second squared times seconds is equal to meters a second, which is what velocity is. So this is how you can kind of check your work sometimes, is just using the units and seeing if they cancel out to what they should be. Okay, nonetheless, let's keep going on. So a dt is equal to v. What happens if we integrate both sides? By the way, that should be a dv. Don't forget your d right here. This is a differential amount of velocity, right? So dv. Okay, a dt is equal to the integral of dv. And this just, there's an imaginary 1 here, so imagine you're just integrating 1. It's not imaginary, it's a real number, but I didn't write it because nobody writes down the number 1. Okay, so what's your bounds? Read the question here. Well, I mean, read the information. Initial velocity VO, okay. So we put VO over here. Let's write that in blue. So VO goes here. And then, oh, final velocity, so that's our top bound here. And acceleration is constant. And it starts at some time t equals 0. Okay, so 0. And then we don't know what the top bound for this integral is. Well, look at it. It's a dt. A dt. So this is integral talking specifically about time. Now we don't know what time we're going to end at, right? We don't know a number here. Well, we just know that it's going to be some time t, right? Just like this is just going to be some velocity v, right? Okay. So if we integrate, what happens? Well, we get a t to 0 is equal to v VO. This is just the integration, right? This is just calc 1 right here. Okay, so let's do it. Let's apply these conditions now. We get a t, right? Because this is just a 0 here, so you plug in it, just at is equal to v minus VO. Okay, and then now what happens? All of that, look at that. You go v, add this VO on the other side. You get VO plus AT. And there we are. All of that. That's where these equations come from. You're just using these simple true facts, right? And just applying the logic, going through with it. Okay, so how do we get this equation now? Well, we're going to use this equation, and we're going to use these initial conditions, and we're going to use one more fact. So we're going to use the fact that v is equal to dx dt. And then we're also going to use the fact that v was what did we say v was equal to? We also said v is equal to this. Okay, so if all those things are true, let's just focus on this part. So if we just focus on this part, what if I put dt on this side and leave dx over here? So we get dx is equal to VO plus AT dt. So it's like the same thing we're going to do again, and now we're going to insert an integration. So we're inserting our integral, right? As long as you integrate both sides, I mean, it's the same thing, right? I mean, you're doing the same thing to the other side, right? That's how math works. And what's our conditions here? Okay, it starts at XO and travels to position X, okay? So we get X, we get XO over here. That's our bounds, right? I mean, that's perfectly true to say. I mean, that's what our condition's saying. And then this is saying it travels from what? T to 0, okay? So this is going from t to 0. And this makes sense because it's a dx integral and our bounds are x. It's a dt integral and our bounds are t and 0. Okay, well if we integrate all this, what do we get? Well, we get x from what? X to xo is equal to VO plus, oh, remember this is an integral, so there will be a t here because it's integrating, right? That's how it works. Okay, and this is AT, so it's become AT squared over 2, and you're going to integrate it from t to 0. Okay, so now if we just apply these in, right, what do we get? We get x minus xo. Okay, that's this one, right? And let's apply this. Okay, if we apply it, just stays the same, really. But let's write it like this. Oh, wow, look at that. It's all starting to get really close already. So what do we have now? We have x. And let's put this let's put this xo on this side. So we get xo plus VOT plus 1/2 AT squared. There we go. We're back at this equation now, right? Same thing again. We just use what we know. We apply the logic that's given of the, conditions, right? We apply that logic. We perform a little bit of integration, and then we get our equation. Let's do another one. Okay, and now if I'm being honest, it's going to be the hardest one to actually find, right? Let's go back and see if we have any tips. Okay, here's the tip. We're going to use this information. We could also use this information. This is like the shortcut way of saying all this, right? So let's use this. Let's use this information right here. So a dx is equal to v dv. Okay. Well, what do we do with this? What can we do with this, right? That's the question. Well, we can apply our integration. So we go a dx is equal to the integral of what? V dv. And what are we given? We're given that we start at some position xo, and it goes to some distance x at the end, so this is our top bound. And what about velocity? So we start with the velocity VO, okay? What else? And then we reach a speed V, so this is our final speed, V, okay. So then if I integrate, and if I do it properly, okay, A is not a function of x, right? A is not a function of x, right? Assuming that this is just some constant, right? That's why all of this works, is because we said acceleration is constant, so this will work. Okay, so this goes A x from V to VO is equal to what? Well, this is the integral. This is V dV, so we do have to integrate here. It's V squared 2. And this is from what? V to VO. Oh, my bad, this is not. This one's x, and this one's x. Okay, so now if we apply this, if we apply all that, what do we get? Well, we get A goes from, A is multiplied by x minus xo, and we get that. Okay, let's put the 1/2 out on the outside, and then this v squared, it'll become v squared minus vo squared. Okay. What's a way to say x minus xo? We could say it's a times change in x, right? That's what we could say. And yeah, actually let's leave this 1/2 right here. We won't skip steps. Okay, and we want it to look like this, right? So what can we do? We can times the 2 on the other side. That'll go like that. Okay, so now we got 2a change in x is equal to what? Well, there's a v squared on this side, so we'll leave the v squared on this side. And then we'll add the vo on this side, the vo squared on this side, right? And look at that, there we are. We got our equation again. It's exactly what we wanted. That's exactly what we predicted, right? Okay, well, this is going to be our first real problem. No more derivation. Yeah, I can't say that word. Okay, so we want to find the position and the velocity of a rock just falling down a cliff, right? Oh, okay. Well, actually, we're standing at the edge of a cliff, and then we throw it up. So just pretend we throw it straight up, like that's possible. Like you just like go like that with the rock. So you throw it up with, let's call that VO, say initial velocity VO is equal to 13 meters a second. And then the rock misses the edge of the cliff as it falls back down to Earth. Okay, so we throw it straight up, moves like a little bit, and then it just falls straight down back to Earth, down like some valley. Okay, and we want to find the position, the velocity of the rock at these times. So we'll go T1 is equal to 1, T2 is equal to 2, and T3 is equal to 3. And there's no air resistance, so that's good. Okay, now before we start this problem, this is going to be the most important thing you actually do. Do we define our coordinate system as positive up here or positive down here? What do we do? Now, you could pick either or. Now the fact that I said VO is positive, if I said VO is positive since we're throwing it up, that means that we're going to call upwards our positive direction, and we're going to call downwards our negative direction. Okay, so then what does that mean? Well, gravity, what direction does gravity go? Gravity goes downwards, so gravity is negative. So gravity is negative 9.81. Okay, so that's important. Okay, now let's think about what equation to use. We're given a velocity, initial velocity, we're given gravity, and we're given time. We want to find position. Let's go to our equations. Okay, this will tell us final velocity if given initial velocity, acceleration, and a time. So that's good. We can actually find our velocity with that. But first thing we want to do is find our position, our change of position. Let's maybe use, I think maybe we should use this equation. Okay, because we want to find position first. We want to find its final position. Okay, and by the way, it said that like assuming, this is the important exception to make, and let's use y instead of x because we're talking about vertical, right? That yo is equal to 0, right? We're not standing, I mean, we're standing on the cliff, right? But for this diagram, this is the edge of a cliff, right? So important note to make is that we're standing right here. And so we're standing at the origin, right? Here's the origin, right? And if we throw it up, and then it just falls down, right? So we're good, okay? And our position vertically is yo, and yo is equal to 0. Okay, so these are all important assumptions, not important assumptions, important facts to find that are given. Sometimes you have to make an assumption to find these facts, right? Okay, so we want to find y, we'll go y1, y2, and y3. We want to find all that. Okay, and the equation we're going to use is y is equal to yo plus VOT plus 1/2 AT squared. So this is our general equation we're going to use, and let's adapt it to us. So it's going to be what? It's going to be 0 because yo is 0. VO is positive 13, so it's 13t, right? There's t here. And then 1/2. Acceleration is gravity. So it's going to be gravity negative 9.81, right? It's going to be 1/2 times negative 9.81 and t squared. So this is the equation we're going to use to find these three positions. And all we got to do is just put in the times. So we'll go like this. y1 equals, well, let's do this. If t is equal to 1. If t is equal to 2. If t is equal to 3. y1 is equal to, y2 is equal to, y3 is equal to. Okay. So let's just insert 1 second into this. So we get 13 times 1 plus 1/2 negative 9.81 1 squared. What's the next one? We're going to get 13 times 2 plus 1/2 negative 9.81. We're going to get 2 squared at the end here. We're squaring time, right? And we'll go 13 times 3 plus 1/2 negative 9.1 and 3 squared. And let's write down this answer. Now I'm going to pause the video and get you guys the answers. Okay, so this is our final positions for y1, y2, and y3. Let's just talk about this. So this means that when we threw the, like, for just 1 second at a time, right? So just 1 second at a time as we threw the ball up, it just, 1 second, after 1 second, it was 8.1 meters above our head, right? Okay, that makes sense because it wasn't that much time, so it should still be up in the air. Okay, now add a little bit more time. It means that the ball is still in the air, but now it's starting to come back down. So it's going to be 6.4. It's going to be a little bit closer, right? It's coming back down to Earth. Here, y3, what does this mean? So it means after 3 seconds of time, the ball went fully up into the air and now is below us. So it's now past the cliff. It's off the edge, right? So it's important to understand that these answers do make sense. Okay, now our next goal is to find V1, V2, and V3. That's what we want to find. Now we don't know what that is, but how can we use that? What equation will we use to find it? I think I said it earlier. Okay, so if we know, we want to find V squared. This is going to be kind of useless to use because we know time, we know acceleration, and we know initial velocity. So why don't we just use this equation? This won't even tell us anything for the final velocity. This will tell us something, but it's not the most efficient way to go about it. So we should probably use this one, right? We should use this equation. So we're going to use V is equal to VO plus AT. And let's make this equation specific for our situation. So V, we don't know what V is. We'll find it. But we know what VO is. VO is 13. It's positive 13. And then what's gravity? Well, gravity is going to be negative 9.1. So it's going to be plus negative 9.1. And times some time t. And this is our time t. So, right, let's do it again. If t is equal to 1, if t is equal to 2, if t is equal to 3, what happens? So we'll get 13, 13, 13, plus, 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 and we're going to go negative 9.1 times 1 is equal to what? Same thing here, negative 9.1, but what? What's the t here? T is 2. And we get negative 9.1 times 3. So we're going to input all these values, and then we're going to see what's our velocity at this position, because this tells us our velocity at this position. Okay, so here's our velocities, right? This tells us that at that moment when t equals 1, it's still actually, the rock is still going up in the sky. It's still traveling positively up there. At t equals 2, it tells us it's starting to come back down, and it's starting to come back down at 6.6 meters a second. And for t equals 3, it's telling us it's starting to come back down really fast, right? And that makes sense because it's already past the origin, right? And by the way, you define the origin where you want. But remember, if you define it where you want, that means that you have to define what's positive and what's negative. And we did do that. So this makes sense. So let's give it a red blocks because it's correct. A check mark. So that's all good. All good. Okay, this next question should be kind of fun, right? So we're gonna see that we have a car and we want to know when it's gonna stop, right? Like how long it takes for it to stop, and maybe the distance that it skids, or it's the distance it travels before it actually stops. So we know if it's on dry concrete, so if it's not raining, it can decelerate pretty quickly, right? It can decelerate. So A, it's not raining red. So A is equal to what? So we're saying decelerate. So I mean, let's say it's negative. It's negative 7. And then we'll call this A1. And then A2, they're telling us if it was on wet concrete, it's going to be negative 5 meters a second. Okay. We want to find the distance necessary to stop if the car was moving at 30 meters a second. So we're going to say VO, and VO is the same for both, right? Is equal to 30. Okay. And we're going to repeat both these calculations and find the displacement of the point from the point where the driver sees the traffic, he sees the red light, and then he reacts. Okay, so we are given, and we'll call this TR for time of reaction is equal to 0.5 seconds to get his foot on the brake. So it takes him half a second to actually put his foot on the brake after he sees the red light. And he's traveling at 30 meters a second initially. And then he's going to hit the brakes, and depending on what surface he's on, he's going to decelerate. But we should make the assumption that, let's see, read the question. How far does the car go when coming to a halt? what does a halt mean? Halt means he stops. So it means that V final, whatever our final velocity is for both of these, 0. He stops, right? He stops at the end. So let's think about how we can find, what's the first thing we want to find? Find the distance necessary to stop a car. Okay. So let's make a note here real quick. Task one, just find change in x, right? We're just finding the distance it takes him to stop, right? Because he has to slow down, so he has to travel some distance. And then task two, task two, we want to repeat both calculations, finding, okay, and then we're going to factor in his reaction. Factor in TR, which stands for reaction time. TR is our reaction time. Okay. So we have actually like multiple little problems going on in this one problem. Let's try to solve for, let's think about what equation to use before we solve. It's always important to actually think about what equation you use. So we probably are going to use this one. I just note because remember I wrote down change in x and we want to find change in x. I mean this is also change in x, but we don't have a time. This one has no time. It's not dependent on time. We know what v squared is. It's 0 squared. We know what VO squared is. It's 30 squared. We know what acceleration is. They literally wrote it down. That's the first number we wrote down. But we don't know what change in x is. So you pick the equation that only has one unknown because why not, right? You want to make it easier for yourself. So let's go back and write this equation in black. So v squared is equal to VO squared plus 2a change in x. This is our equation, but we want to make it special to us. So if it's special to us, it's going to be 0 is equal to 30 squared plus 2. Now it's either going to be a1 or 2 and change in x. Okay, so this is what we're actually going to use right here. This is the general form. So what we're actually going to use. Now we want change in x. So maybe we should try to solve for change in x first. So change in x is going to be equal to what? Well, there's a 30 squared on this side, so let's put the 30 squared on the other side. So we'll go negative 30 squared, and then let's divide by 2a. Okay, so we're going to use this, and then we're going to have these two answers. So on wet, actually let's do dry first. On a dry surface and on a wet surface. So change in x is going to be negative 30 squared. The negative's on the outside, by the way. Like this negative is not part of 30, right? It's on the outside. If there's a parenthesis here, then it would be positive. Our answer would be positive, but no, the negative's on the outside here because this is algebra, right? You can't forget that. That's how algebra works, right? That's just how it works. Okay, and divided by what's a? On a dry surface, it decelerates at -7. Okay, so we'll put that in the calculator in a second, but let's find this one. It's going to be negative 30 squared divided by 2 times, what's a in this case? It's -5 here. Okay, so I'm going to make these answers magically appear. Okay, now we're on to task 2. So this is actually going to be like the hardest part of all the questions we did so far. Let's think here. So we got to factor in TR. And let's just think what this really means is he's driving. He's traveling at some constant speed. And he doesn't see the red light, so it takes him some time to see the red light. And then he hits the brakes and then he starts decelerating. So there's the equation we can use to describe all this. It's going to be, it's not that one, it's going to be x is equal to xo plus VOT plus 1/2 AT squared. Now this is before he hits the brakes. So he's traveling at a constant speed before that, right? He's just traveling normally. You're just driving your car normally. So A is equal to 0. Thus we knocked that out. So we're just left with x is equal to xo plus VOT. And by the way, there's another way to actually think about this equation. So we say recall V is equal to VO plus AT, right? So this is like, it's kind of like it's like little, this is like its little brother, right? This is the big brother, this is the little brother. They're very similar, aren't they? Now, but this is the logic behind this equation, right? If you don't have the acceleration and you just need to find the initial position and that position he travels, you would use this type of equation. And this is not usually included in our general formulas because it's not a true general equation. This is actually a very specific equation, right? This is very specific to our situation. Okay, nonetheless, we're going to find x because he does travel some distance before he hits anything. Okay, so x, and xo is 0, so 0. VO is 30, right? He's traveling at 30 meters a second, right? And TR, so this is, let's write this as TR here. Okay, so 30 times 0.5, and this is 15. So he travels 15 meters, right? 15 meters before reacting. Okay, so this is important. We need to factor this into this equation. Specifically, this equation. We can reuse most of this, we just got to make a minor change. So change in x is equal to x minus xo, right? And earlier xo was nothing, right? That's right in blue. Maybe I should have said that earlier. I hopefully hope that it was implied. Xo is equal to 0, right? That's why this is just changing x is equal to x. And let me just write equals x here. X, wait, that's x dry, x wet. Okay, so this is going to be x react, x react dry, and x wet. Okay, so x, we don't know what x is, but we do know that xo is 15. So when we use this equation, we have to modify it. So it's going to be x is going to be equal to, x is going to equal to negative 30 squared divided by 2a, but then plus 15, right? We're just going to put the 15 on the other side to make this equation valid. So it's very similar to this one. And then we're going to have a dry and a wet. Right, so what will this be? This is going to be 64.3. We know it's 64.3, but it's going to be plus 15. And this one's going to be 90 plus 15. And what's that? Let's do this math here. We don't need a calculator for this. This is 64 plus 15. That's going to be 79. Right? So 10 plus 60 is 70. 4 plus 5 is 9. There's a 0.3. And this is meters. And then this one is going to be 105 meters. And this is equal to what? What is this equal to? What are we naming this? This is x r wet. And this we'll call this x r dry. So this would be how much he would travel. This would be how far he would travel if it took him a half a second to react, and if the road was dry. This would be how long it would take him to this would be the distance he would travel if the road was wet and if he took a half a second to react. So this question was pretty in depth, and I thought it was a really good exercise to teach these concepts. Okay, So if you got these correct, I mean, good job on you. Consider subscribing and liking if you found this video interesting or helpful. Leave a comment. Just leave any comment, just so I could, get this video pushed up in the algorithm.